Hello everyone, I'm Yuxuan Du from the University of Sydney. Here I'd like to share our recent work, Quantum Circuit Architecture Search, Error Mitigation and Trainability Enhancement for Variational Quantum Solvers. This work is completed with Tao Huang, Shan Yu, Min Xiuxi, and Da Cheng Tao. As we can see, the fabrication of quantum hardware has achieved a big success in recent years. To date, we can access 65 qubits quantum chips, and maybe 3 years later, we can use 1000 qubit quantum devices. In other words, we are stepping into the noisy intermediate scale quantum era, which is also known as NISQ era. However, there are still some qubits of NISQ processors, which are a limited number of qubits, a shallow circuit depth, a connectivity restriction of qubits, and unavoidable system noise. To alleviate these qubits, the variational quantum circuits or equivalently quantum neural networks are proposed. Recent studies have employed variational quantum circuits to achieve machine learning, chemistry, quantum info processing, and quantum metrology tasks. Formally, the variational quantum learning scheme problem can be formulated as follows. Given an input Z and an objective function L, where the variational quantum learning scheme employs a gradient-based classical optimizer that continuously updates parameters in a trainable quantum circuit U theta to find the optimal parameter theta star. The optimization problem is described by this optimization function. As we can see, it's a trace function, where the notation C stands for the constraint set. Theta are adjustable parameters of quantum gates, and the state phi theta are prepared by the trainable quantum circuits U theta. However, there are still some changes to optimize variational quantum learning scheme, which are the baryon plateaus and the large system noise. As we can see in this figure, the global optimal of the variational learning scheme is located here, but when the variational learning scheme encounters baryon plateaus or large system noise, the optimized parameters theta t is located here. So there is a big distance between the optimized parameters and the optimal parameters. Under this setting, we say the optimized result is collapsed. To improve the trainability of variational quantum learning scheme, some solutions are proposed. In particular, to avoid baryon plateaus, we can modify the cost function. For example, we can substitute the global measurement operator with a local measurement operator, and we can also adopt certain strategies to initialize parameters. As for the suppression of quantum system noise, we can employ advanced quantum error mitigation techniques such as zero loss extrapolation methods, the subspace expansion methods, and the learning Clifford sequence-based methods. However, we notice that these two methodologies are generally separated, which means that the solutions addressed baryon plateaus cannot apply to error mitigation problems and vice versa. So this motivates us to rethink if we can unify the elimination of baryon plateaus and the mitigation of the quantum errors in a single problem. And our answer is yes. Before presenting our solution, we'd like to give some intuitions. As we can see, will we increase the circuit depth, the expressive power of the trainable circuits U theta is increased. However, the price is introduced baryon plateau phenomenon and induce accumulated large noise. This means that the optimized result theta t is far away from the optimal result theta star. Conversely, if we decrease circuit depth, we can see the baryon plateaus for the mirror is negligible. Similarly, the cumulated noise is small. However, the expressive power of your theta is decreased. This means that the optimal result theta t is still far away to theta star. So based on the above observations, we want to find a good circuit architecture which can obtain sufficient expressive power but not introduce too deep circuit depths, which can avoid baryon plateaus and control the introduced system noise. So based on these intuitions, we can reformulate the problem of variational learning scheme to improve the trainability and mitigate errors. Formally denote S as the set that contains all possible circuits to build the trainable circuit U theta. Suppose the quantum system noise induced by the employed circuit architecture A is modeled by the quantum channel epsilon A, considering the circuit architecture, information, and the related noise. The objective function of variational learning scheme can be rewritten as this one. As we can see, instead of only pursuing the optimal parameters in the reformulated problem, we also want to find the optimal circuit architecture A star. We remark that the brute force searching of the optimal architecture is invisible. This is because the total number of circuit architectures exponentially scale with the qubits count n and the circuit depth L. For example, as shown in this figure, when a single qubit gate can be sampled from these 8 gates, and the 2-bit qubit gates can be sampled from the controlled X, controlled Z, and the controlled identity, the total number of circuit architecture is 8 to 3NL times 3 to NL, which implies that the exponential scaling with respect to the number of qubits and the circuit depths. So to avoid the brute force searching, we propose the quantum circuit architecture search scheme, AQIS, to tackle this optimization problem. Notably, AQIS can efficiently and automatically search the optimal circuit architecture to avoid baryon plateaus and sparse errors. Meanwhile, the runtime cost of AQIS is almost the same with conventional variational quantum learning algorithms. The paradigm of AQIS is as follows. It includes 4 steps. In the first step, we set up a supernet, and in the second step, we optimize supernet, and in the third step, we rank k subnets and pick the one with the top performance, and in the last step, we retrain the search subnet with few iterations and output the optimized result theta t. In the following, we explain the QoS step by step. In the first step, we set up the supernet and adopt the weight sharing strategy to initialize parameters. The supernet is an abstract concept inherited from the deep neural network architecture search. The aim of the supernet in AQIS is manipulating all possible quantum circuit architectures of the trainable circuit U theta, training them efficiently and outputting the candidate with the best performance. AQIS also adopts a weight sharing strategy to avoid training each subnet from scratch and to force all subnets to share trainable parameters. In doing so, the runtime to seek the optimal subnet from exponential subnets is dramatically reduced. For ease of description, here we only focus on the else layer. As we can see, if the two subnets highlighted by the green region share the same gate arrangements, then the trainable parameters in these single equipped gates are shared. Conversely, as we can see, if the gate arrangement in a subnet is different with above two subnets, then the trainable parameters of this single equipped gates should be trained independently. Once the supernet is initialized, we can optimize it. In particular, we repeat the following step with t times. And in each iteration, we uniformly sample a subnet A from the all possible circuit architectures, and we follow the conventional optimization of the variational quantum circuits to optimize its trainable parameters. Meanwhile, following the weight sharing strategy, the update parameters will also influence the subnets share the same gate arrangement, and we repeat this procedure with t times. After optimization, we run k subnets. Specifically, quasi-uniformly sample k subnets and rank their performance and assess the subnet with the best performance as the output to approximate the optimal architecture A star. In the last step, we use the sampled architecture and retrain it with few iterations to output the optimized parameter theta t. In the training procedure, we find a phenomenon called the fierce computation, which means that when we independent training all subnets, its performance is contradicted with the performance training with QuAS. For example, there are two circuits showing the left figure and the right figure. And with the independent training, we find the classification accuracy of the left one is 99%, which is higher than the right one. But when we use QuAS to train these two circuits, we find that the right one achieves a better performance. So to alleviate this issue, QuAS employs W supernets instead of one to conduct the training, and we prove this solution is optimal in the measure of regret. Here is our simulation and the experiments to use QuAS. The first one is using QuAS to achieve classification tasks. And we can see the figure B is the conventional quantum classifier, and the figure C is the search architecture of QuAS. As we can see, QuAS use few single qubit and two qubit gates. And the figure F illustrates their training performance. As we can see, under the noise setting, QuAS can still achieve 100% training and test accuracies. But for the conventional classifier under the noise setting, it can only achieve 50% accuracy, which implies it only conduct random guessing. This result reflects the power of QuAS. We next apply QuAS to achieve the ground state energy estimation tasks. Namely, we want to find the minimum eigenvalue of this Hamiltonian. And we also compare the performance of QuAS with the conventional quantum eigensolver. And here, the figure C and the figure D illustrate the simulation results. And we can see for the conventional eigensolver, the training performance only converts to minus 0.4. But for QuAS, it's very close to the exact result. It achieves minus 1.1. And we also test the how QuAS to address the baryon Plato's phenomenon. As we can see, Conventionally, for conventionally quantum variational circuit, the variance will exponentially vanish with respect to the circuit depth. But this is not the case of quarks. As we can see, when the circuit depth is increased, the variance can also be increased. We last implement quarks on real quantum device to benchmark its performance. Here is the simulation result. As we can see, quarks achieves a better performance than conventional variational quantum mechanical solver. And we can also improve performance quarks by using advanced strategies in the ranking stage. And we can also adopt a bandit learning algorithm to train multiple subnets. So in the future work, we will design more advanced weight sharing strategies to reduce parameter space, and we will also leverage private information of noise model to boost performance of quarks, and we will also theoretically the understanding of the fierce competition. Thank you.